Hello, this is the second week, a lecture on measuring time. And measuring time means building clocks. Now, interestingly enough, there are lots and lots of clocks, many different kinds of clocks. In fact, going back to the early days of, I think maybe the early days of agriculture and the early days of astronomy, there are lots of clocks around, and clocks are actually vital for agriculture. So, by a clock, we usually mean whenever something repeats, like when a clock goes tick, tick, tick. The time interval between the clicks, that is the period of the period of the clock, and that measures time. So, for example, the moon going around the Earth is a monthly clock. And then Stonehenge is a yearly clock. Also, the Earth going around the sun is a yearly clock. In fact, you might say it's very, very fortunate for us humans on Earth that we have a yearly clock, which is the Earth going around the sun. And then we have that 1 year is broken up into 12 or so different sub-pieces given by the moon going around the Earth. So it's very easy now to do agriculture. If you have a way like Stonehenge of knowing when the summer solstice is or the winter solstice, then you can count your moons from that time to when, for example, the berries will be ripe or you're ready to plant your seed and so on. So those are natural clocks, astronomical clocks. And in fact, because they're so regular and actually so beautiful, if you're out on the desert in North Africa, for example, and on a desert on a night, pitch black night, moonless night, the stars are really very vivid. And when we live in cities with all the city lights around, we sometimes don't see how vivid the stars really are. But it's really a spectacular thing. And it's not surprising at all that humans then began astronomy by measuring, for example, the passage of the stars across the night sky. So here are various different clocks. There's the solar system clocks, and that's, for example, the Earth's rotation, which is 1 day. The Earth's rotation around the moon's rotation around the Earth, which is 1 month, and 1 year, the Earth going around the sun, which gives us our seasons. And so it's that variation of the seasons that tells the person when a year has passed. If you live near an ocean, you have also 12-hour clock, which are the coastal tides. Okay, so those are all there. Just really rather beautiful constellation of clocks that are just easily available. Then there are human body clocks, for example, a heartbeat, your pulse. And there's also a voice clock. Children will count out 1001, 1002, 1003, and that's a rather nice clock, actually. You can test that out and see how accurate that clock will tell time. Now, there are actually other primitive clocks, too. For example, there's the sundial. As the Earth turns around over a day, if you have a vertical stick, or a vertical tree, or it doesn't have to be vertical, actually, as we'll show in a minute. You just have to have something sticking up that casts a shadow, and that shadow is a sundial. And so now, if you mark off periods, then the next day, the shadows will follow almost exactly the same pattern, and you can use it as a day-to-day clock. There's also like a drip clock. I think, in fact, if you take a leaky faucet in your kitchen or bathroom, if you take a leaky faucet and adjust the faucet so that it just drips like drip, 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 like 1 per second, that makes an excellent clock, actually. Rather excellent clock, because the pressure of the water is the same and the opening of the drip is the same, and so it's a very steady, accurate clock. The really good clocks, however, the accurate ones, the easy ones, are so-called oscillator clocks. Now, anything that's elastic will vibrate or oscillate. So, for example, you take anything like a spring, for example. We stretch a spring, let it go. Or if you put a mass on a spring, let it go, it'll oscillate up and down. Or if you take our ruler, if you take our ruler, for example, and put it over the edge of a table, bend it down, and it'll oscillate and back and forth. So whenever you have a elastic material, essentially everything made out of atoms is elastic at some level, you disturb it from its equilibrium position, and it'll go back to its equilibrium position. It's called the restoring force. And the easy ones are, for example, a pendulum. A simple pendulum is just a mass hanging from a string. A physical pendulum is like a rod or a grandfather clock. And a torsional pendulum is a pendulum that actually twists around, goes around. And so we'll see pictures of that. A rod or a bar that is held over the edge of a table and bent down and let go. That'll oscillate. It's not a very good oscillator, but it'll oscillate. The mass on a spring is one thing we will do in somewhat more detail a little later. And then there are atomic clocks, which are actually they're oscillations of the electron clouds. They're oscillations of the electron charge distribution within atoms or molecules. Okay. Now there's some weird clocks, like the capillary clock. If you take a piece of cloth, put one end of it in water, and the other end goes up and over attached to something up above, but then hanging down on the other side, you may have to put a pin there so that the water will gather at the pin and then drip off the edge of the pin. But that's a capillary clock that works by capillary action, which is a force that works against a molecular force, really, that works against gravity, and water will wet up the cloth and go over the top. Now, the Rube Goldberg clocks are just various contraptions, very clever contraptions, but never mind. They're also chemical clocks. There are several chemical reactions that you can go act in sequence. Each of them has a reaction time. So, for example, a solution may be green, and then it turns blue, and then it turns red, and it turns purple, with very fixed times. And that's because chemical reactions at a given temperature have a certain reaction rate. There's also a heat engine clock, like a dipping duck, for example, is a heat engine cycle. So here's some rather old sundials. For example, the one up on the right-hand side is actually mounted on a vertical wall. Okay, and there's a little stick sticking out. You can maybe not barely see it, but it kind of goes down at the 7 o'clock position, and then the hours of the day are written out here. And that's a good sundial. And then you can also put a sundial on the ground, and here's again a post sticking up, and it casts a shadow, and then you see there markings around. There's east and northeast and north and so on, and you can tell the time of day from this. Now you should try some of these, okay, just for fun. A voice clock, okay, or a heartbeat clock, just to get a feel for what it's like. Capillary clock may be a little awkward, and you can just look up Rube Goldberg clocks. But a sundial actually can be made in the classroom and moved outside. A small one, for example, like the skewer, for example, could be just poked vertically into something like, for example, I guess in the week 14, there's a 1-inch foam piece, and you can use that as a base, and you stick the skewer into it at any angle you like, and then put it on a piece of paper and just mark where the shadow is, for example, at 15-minute intervals. And so every hour you maybe make a bigger mark, for example. That's a perfectly good clock. Okay, but you can also use a flagpole or the corner of the school building. Okay, and if you make markings on the ground at certain specific times, then the next day you go out and you see the shadow at some marked position, you know what time it is. Okay, so those are sundials, basic sundials. So now here's a restoring force oscillator, the simple pendulum. In fact, I think I will demonstrate this in just a second.